Geometry. Welcome to our next section in right triangle trigonometry. We're going to actually look at applying those simplifying radical concepts from last time to the sides on a right triangle. We've mentioned the Pythagorean theorem before, but we're going to spend a little bit more time on it, go a little bit more in depth. Now, the way the Pythagorean theorem was originally conceived was well, maybe not one of the originals, but how the Pythagoreans thought of it, because they didn't have geometry, or they didn't have algebra yet, was they said, all right, the two legs, if you put a square on the end of each leg that has that leg as a side length, and you do the same for the hypotenuse, the squares of the legs their total area is the same as the square of the hypotenuse. So if you add A's square and B's square, you get C's square. So we express this in algebra as A squared plus B squared equals C squared. The squared operation being A times itself, B times itself, and C times itself. So the important bit about this is that B are both the legs. A is a leg and B is a leg. These are the legs on our right triangle, and C is the hypotenuse. Hypotenuse. Oops, that's not how you spell hypotenuse. Hypotenuse. There we go. Hypotenuse. The hypotenuse is the side across from the right angle. It's the longest side of the right triangle. The longest side, the hypotenuse. So A squared plus B squared equals C squared. A and B are free to switch. A can be the first one, or B can be the first one. It doesn't really matter. C needs to be the one that's by itself, though. A's square and B's square total to C's square. So we can use this relationship. This is true for any right triangle. We can use this relationship to solve for a missing side length. So in this one, C, there's our side across from the right angle. That makes 5 and 12 the legs. So the 5 could be A, and the 12 could be B. So 5 squared plus 12 squared equals C squared. We use this formula each time. So this formula is we're going to write every time. A squared plus B squared equals C squared. 5 is A, 12 is B, C is C. So we'll simplify. 5 squared is 25. 12 squared is 144 equals C squared. Add those together. And they're on the same side of the equal sign. You just use the operation that's there. 169 equals C squared. We're going to take the square root of both sides. Once we get the C squared by itself, just like with the distance formula or with finding the R in a circle, once we have the C squared by itself, we take the square root to find that. In this case, C is 13. Oops, that should be an equal sign. C is 13. Okay, remember the square root of a square gives you just the number underneath. So 13. So our C is 13. So 5, 12, and 13 are the sides on a right triangle. We can do this even with square root expressions. If this side length is the square root of 7, that's like 3 point something, right? This 2 squared is 4, and 3 squared is 9. So 7 is, or the square root of 7 is something like 3.5-ish. So we're going to still use the Pythagorean theorem, that A squared plus B squared equals C squared. This will be our A, this will be our B, this will be our C. So the square root of 7 squared plus x squared equals the square root of 19 squared. And what's nice about using square roots as the expression instead of using a decimal approximation is square roots and squares just cancel each other out. The square root of 7 squared is just 7. X squared is still x squared. And the square root of 19 squared is just 19. We can subtract 7 because we're solving for x squared this time. That was our B. So we get 12. And then take the square root of both sides. So x is the square root of 12, which we then need to simplify using our strategies from last time. 4 goes into 12 3 times, and then the square root of 4 is 2. So 2 root 3 is our third side length there, 2 root 3. Do the same thing here. You can do the same thing here. 7 is our A, B is our B, 10 is our C. So 7 squared plus B squared equals 10 squared. 7 squared is 49. B squared is B squared, and 10 squared is 100. We can subtract 49. B squared equals 51. And when we take the square root, B is, well, 51 doesn't have any perfect square factors. Its only factors are 3 and 17. So square root of 51 gets to stay the square root of 51. And we're going to leave our answer as a simplified radical. Now, we can use this to find missing side lengths in right triangles. And right triangles even where we've constructed the missing side. So if we know this is 29, we know this is 26. And if we draw the height in this triangle, well, areas of triangles have that formula, base times height divided by 2, or 1/2 times base times height. If we don't know what that height is, well, we can use the Pythagorean theorem to find it. If this is a right angle here, then this is a right angle. So our 11 could be A, H could be B, and then 26 could be C. And we can find that height in order to find the area. So our height then, H squared plus 11 squared equals 26 squared. H squared plus 121 equals 26 squared, which, let me get the calculator out here real quick. 26 squared. 26 squared is 676. 676. We can subtract, and then we find that H squared is 555. And then I think that doesn't have any perfect square factors. So when I go to take the square root of 555, if we're not sure, we can just go through some of the let's see. Yeah, if I tried dividing that by 5, let's see, 555, let's do this here, divided by 5, because it ends in a 5, so that occurs to me like that. 111, I think, is divisible by 3. And 37 is prime. So 3, 5, and 37, all prime, no repeats, no perfect squares. So this is as simple as that gets. So height, square root of 555. In order to find the area, I'm also going to need to know the base, which is this full side length. And if I don't know that side length, well, if I know the height, and I know this side length is 29, I can find this other side here. So I could say b squared plus the square root of 555 squared equals 29 squared. And another great thing about this being using that perfect square notation, or that square root notation, is when you square a square root, it just gets rid of the square root sign. I didn't have any decimals that I needed to worry about. B squared plus 555 equals 29 squared is 841. So we'll subtract 841 minus 555 is 286. And let's see, I don't think that is divisible by anything. Yeah, we'll just leave it like that. Okay, square root of 286. If I divide it by 2, I get 143, which I don't think has any, let's see. Yeah, not divisible by, it's not even, it's not divisible by 9. I think, yeah, Yeah, I don't think that's going to be divisible by anything, not going to be factorable. So we'll leave that as our square root of 289. So our area, back to our area. Our base length is not 289, it's actually going to be the 11 and the 289 put together. So maybe we'll, for the sake of this one, when we're adding numbers and or integers and square roots, we might want to get a decimal approximation. So area equals our base, 11 plus the square root of 289. We're going to multiply that times our height, square root of 555, and then divide by 2. So this would actually be an exact representation of the area. Well, if we get a decimal approximation, if we take the square root of 289, square root of 289. Oh, actually, sorry, 286. Square root of 2, not 289. Square root, let's clear that. Square root of 286. Yeah, it would have been nice if that was 289. So square root of 286 plus, oops, let's close that off, plus 11 times the square root of 555 divided by 2. So 328.77, or 328.78. And they don't give us a unit, so we could just say square units. Something like that. So using the Pythagorean theorem to find missing side lengths is what we're going to be doing in that section. Our next section does something similar, except we're going to be using the converse of the Pythagorean theorem to find out what kind of triangle our figure is. So stay tuned for that. Talk to you next time.